Okay. Hello, everyone. Yeah, but when I talk, something happens with the microphones. Maybe when I'm standing here. Okay. I don't know. But I think still we. Hello. I have to coordinate my hands with the laser and the microphone, so hopefully this situation will resolve. But I'm very happy to welcome you to the tutorial on modern recommendation systems. And in these next 2 hours, I know it is a hard slot, but bear with me. We're going to talk about some very interesting stuff that is going on in recommender systems in the industry right now. So this is me. I'm Georgia Koutrika. I'm a director of research in the Athena Research Center in Athens. Moving from United States to Athens, hopefully this year. And recommenders are, of course, one of my top interests, but I also work in data integration, natural interfaces, natural language interfaces to databases, and so forth. So this is how the tutorial will go. So we are going to talk about a little bit why we want to do recommendations. And then I'm going to talk a little bit about some of the classical recommender systems. The reason is that I want you to get an idea of how things started in the recommendation realm and now where we are and how far we have gone, essentially. And then I'm going to discuss 3 great families of recommendation methods: matrix factorization, multi-arm bandits, and deep learning systems. So why do we care about recommender systems? The reason is that with all this amount of information that we have to deal with every day, recommender systems essentially come to rescue to help us sort through all the available options. And we see recommender systems. Can we switch very quickly? Noise. So there is a noise coming. So I will start talking and, okay then. So recommender systems essentially come to help us in many different websites and many different services, to recommend movies, to recommend products, to recommend our favorite artists on Pandora, or to recommend even people that we may want to connect with. How do they do this? They get information about the content of the products, of the items that we deal with, but also information about user interactions, how the users prefer, how they like the items, and so on and so forth. So recommender systems are valuable both for the customer but also for the provider. For a customer, for a user, they are helping the user to find things that may be of interest to the user. They help him narrow down the options, focus on some few possibilities, but also explore new, novel things that they may not have thought about. Of course, for providers, recommender systems, for example, for Amazon, for Netflix, for Yelp, recommender systems are a valuable, a critical component in their whole operation. Why? Because recommender systems help the provider understand who the user is, what he likes. They help the provider personalize the user experience, promote things, advertise things, but also obtain more knowledge about the user and increase, finally, and ultimately that is the goal, sales, click-through rates, conversion rates, whatever you call this. And just a few numbers, which actually have changed since 2014, that these numbers have been taken for. For example, for Netflix, two-thirds of the movies that are clicked, that are watched, are recommended, so they come from recommendations. For Google News, almost 40% of what news are clicked, these are due to the recommendations. For Amazon's, actually almost 40% of the sales come from the items that are recommended to the users on the Amazon website. So if we take a look at our favorite Netflix site here, we are going to understand that every single piece that we see on this page is actually the result of one or more recommendation algorithms. For example, the banner that we see here is personalized to this particular user. Then all the different categories that we see here are the result of a recommendation algorithm, the order and what it is shown there, but also the particular movies that are shown inside each of these categories are the result not of one, but of many different recommendation algorithms that come together. We combine the results, and hopefully we will capture the user preferences somehow in the best way possible. So what is a recommendation problem in its very essence? We have a set of users, we have a set of items that we want to recommend, and we have some function, some utility function P, that measures how valuable, how useful is an item to a particular user. So what we want to do now is that we want to use all the information that we have in the system, users' past behaviors, similarities between users, similarities between items, the context of the user, and so forth, and be able to predict for every item and the user pair what is the value of the item to this particular user. Ideally for every user, ideally for every item. But now, the very basic form of this problem is the following. You have the users that they give ratings to the items, and you want to predict missing ratings. So this is the most basic form of the recommendation problem. But then, in reality, we don't always have ratings in the system. So we also have other types of implicit signals that we try to interpret as ratings. So for example, the fact that the user bookmarked a URL, that he saved something, that he deleted, that he forwarded this web page to a friend, or maybe that he published it, or maybe that he purchased the product. All these are different implicit signals that can show that the user may be interested in this particular item. So we are accustomed to, we're used to think of recommendations in the context of users and movies, users and items in the general case. But the reality is that the recommendation problem, exactly in the way that we defined it a moment ago, can be seen in many different contexts. And here, let's see some examples from our database community. So the recommendation problem could emerge in problems such as data exploration, query optimization, visualization, workflow design, data integration, and so forth, where the purpose now is, for example, to recommend tuples or query plans to queries, or operators, or maybe exploration actions to users, and so on and so forth. So for the rest of the talk, what I would like to ask you is to forget about having in your mind that the problem of recommenders is just about movies and users. The problem is a general problem of trying to match two different lists of entities. So if you like to think about, you want to find what is the best index to recommend to a particular database design, yes, this could be seen as a recommendation problem. By the way, the works that have been done in recommender systems in the database community are actually very few. And this amount of work really pales if we think all the work that has been done in recommender systems, which is a really multidisciplinary area. So we have here algorithms that come from information retrieval, from machine learning. We have methods from crowdsourcing, from HCI, all these different things that come together and make recommender systems work. So as I promised, for the first part of the talk, the smallest part of the talk, I will just try to give you a glimpse of where recommender systems started from and how the basic concepts of recommender systems have been established. So essentially, I'm going to talk about the two philosophies that we have in recommender systems, content-based and collaborative filtering. I don't intend to go into very much detail into these first methods. I'm going just to show some examples of early content-based filtering and early collaborative filtering algorithms, and that will help us understand why matrix factorization, multi-bandits, deep learning systems are really so cool. So the idea behind content-based filtering is that we analyze what the user has done in the past, what items he has liked, and we try to recommend items that are similar to those past selections. So in our very trivial example here, we have a user that has liked two items, these two items here. So we learn a profile for this user, and this profile will tell us that he likes red things, circular things, and triangles. And then we can use this profile to match to other unseen items and make some recommendations to the user. So this is a very basic, high-level idea of content-based filtering. So how can we do this? The very simple approach goes into 3 steps. So let's consider that we have a user, and he sees all this very big collection of 5 books, and he has already rated these 2 books. The first one and the fourth one, both, by the way, are written by Grisham. So the first thing that we want to do is to make a representation for each item in the database, for each book in this particular case. So we have plenty of options here. For example, we could create an item profile for each book based on the metadata that describe this book, the author, the price, the genre, and so forth. Or we could use the text of each book and make a TF-IDF vector of the most important terms that describe this book. So here, essentially, what we do is that we use a standard information retrieval approach to make a profile for the items. And TF-IDF essentially is a very well weighting scheme for terms from information retrieval, where we measure the term frequency of a term inside the document, but we also capture essentially the importance of this term for this particular document by the so-called inverse document frequency. Now, let's assume that for our very simple example here, we have the books, that this is our collection here, and each row here is a very simple vector of these terms up here, and we just have zeros and one. and ones for simplicity. So these are the book profiles that we have for our data. And now the second step is to generate a profile for the user. And here we can see two options. One option is to use all the profiles of the items that the user has rated, and this will make the profile of the user. So this is exactly what we have here. The user has seen these two items, and these are the profiles for these two items that describe the user profile. The next thing that we can do is to make an aggregate profile out of this. And the easiest way is to aggregate over the characteristics, the terms of each book, taking into account the rating that the user has given to each book. So in our particular case, this would give us this particular profile for the user. We see, for example, that he likes a lot John Grisham because he has read 2 books by this author and he has given high ratings. Now, step 3, we have the item profiles, we have the user profile. How do we match them to generate recommendations? Again, here, the most straightforward approach that has been actually used a lot in practice is to follow an information retrieval way. So here, since we have a user profile and an item profile, we can treat the user profile as a query in an informational retrieval way, and the item as a document, and we can use cosine similarity to find how similar the two profiles are. The score will be the recommendation score that we generate for this item and this user pair, and we can select the top n items to show as recommendations. Again, this is how content-based filtering works, and let's see a simple example here that would give us, for example, this ordering for the books. The highest scored book here is another John Grisham book, and actually here we see one of the shortcomings of this method, that it will always suggest items similar to the items the user has already seen. So the user has no way to see something new he didn't already know. That's why new books from John Grisham will always be rated high for this particular user. Now, overall content-based filtering is a philosophy around how we make recommendations that says that we can take into account the content of the items the user has liked in the past in order to generate recommendations for similar items. How do we do this? We can do it using information retrieval approaches like the one that we described previously, but other approaches can be used. For example, machine learning methods are used a lot in this area. Some of the advantages of this approach is that it doesn't have any item called start problem, which means that if a new item comes in, it can be recommended to a user right away if the user likes this item. It doesn't have popularity bias, so it doesn't matter whether this item is liked by many people or few people. It has a chance to be recommended to the right people. On the other hand, however, as we said, it is very easy to pigeonhole the user because he always sees similar stuff, and serendipity is difficult. So based on these observations here, the next philosophy of recommendation algorithms appeared, and that is collaborative filtering. So the idea behind collaborative filtering is that it doesn't care about the content of the item. It cares about the items. It cares about the usage data, what ratings, what purchases the users made. And we try to recommend items that have similar usage characteristics with the items that the user has already rated, or items from users that have similar preferences with the current user. So we have what we call item-based collaborative filtering and user-based collaborative filtering. And a pure collaborative filtering, the only thing it needs to know is user IDs, item IDs, and ratings. So this is the so-called user item ratings matrix is the purest form of collaborative filtering that we see in practice. Now, just one historical piece of information that I really like. So the term actually was coined in 1992. in a paper that appeared in Communications of ACM and described an experimental mail system that was developed at Xerox PARC. And the basic idea there was that people that are very eager to read emails, we can use these people to help other people read email that are a little more less eager to go and read everything. So this is where the term collaborative filtering was coined. But in fact, 2 years after that, the basic idea of collaborative filtering as we know it up to now was established by this paper, where the idea was the following. People who have agreed in their preferences so far, they are likely to agree again in the future. So based on this assumption, we can build a computational method to generate recommendations. And this is what I'm going to describe next, because it is a very intuitive but simple method. It works well in many occasions, okay? It is a valid baseline method still, by the way, and it helps understand where we have started. So I would like to talk about the user-based collaborative filtering, where the idea is that we try to leverage the preferences of other people that are similar to me, assuming, of course, that I am similar to some people, okay? So these are the items that this user has rated, and we try to find people that have rated the same items in a similar fashion. And from these people, we will choose the most similar ones, and these most similar ones will act as recommenders to this particular user. So the first step in this process is actually to find how two users correlate. And one very well-known metric for this purpose is the Pearson correlation that was published in this particular paper about group lengths, that essentially compares two users based on their ratings. And the idea is that if the ratings of the user, they do not need to be exactly the same, of course, but they need to follow the same trend. So I tend to like the same things, I tend to dislike the same things with this particular user, then our correlation metric, our correlation score will be high. That is going to 1. In the opposite side, in the opposite case, it will go to -1, showing that there is no correlation. Now, how do we choose which users are going to act as neighbors? We can do a threshold. We can choose the k nearest neighbors. And then having this, during serving time, the time that we serve the recommendations, we can do the following. Given that we have a user profile and an item, we can compute how much this user will like this item, taking, for example, the weighted average of the ratings of the similar users for these particular items. So this formula here essentially takes into account the similarity of each of the most similar users to our active user A. It takes into account how their ratings correlate, differ for this particular item, and it also takes into account the average rating of this active user, because we need to take that into account and bring everything together. And again, we can select the top n items to show as recommendations. Now, for this particular case, we want to compare Anne to all other people that their names are not seen, are hidden. And we want to find how much Anne is going to like this item 3. We can use, for example, cosine similarity, or we could use Pearson, but just for simplicity here, let's use cosine. And we see that the top most similar users for Anne are these guys here, or girls, maybe, okay? And based on their similarity, then we can predict a rating, the rating that Anne would give, based on how similar Anne is to these two users, and based on the ratings that these two users have given to item 3. Item-based collaborative filtering is similar to this, has similar steps. The difference here is that we are trying to find items that are similar to the items the user has liked, and based on these items, make recommendations to the user. I'm not going to go into any more detail into item-based collaborative filtering, but the idea, the implementation, if you like, of this idea follows similar ideas as in user-based filtering. Now, all these neighborhood-based collaborative filtering methods are extremely simple, are efficient, and they're able to generate quite accurate and personalized recommendations. And that was great. Up until, of course, items began the item catalog began to be very, very large, up to the point when we start to have a lot of users, and this is where these methods crash. So scalability is one big problem for these early recommendation methods, and another problem that is a problem not only, of course, for neighbor-based, but for all recommender systems is sparsity. Sparsity meaning that we don't really have all the ratings that we would like to have in order to be able to generate recommendations. Even the most active users, they're going to rate only a very small percentage of the items that we have in the catalog, and that creates a huge problem for us to go on. To try to tackle some of this problem, model-based collaborative filtering methods appeared, where the idea here is that instead of computing everything at the moment where we want to serve the recommendations, because that was what was happening up to now, we try to use all the information that we have to learn a model offline, and then use this model to make recommendations. So here we have seen actually a large variety of different methods, from Bayesian methods to deep learning methods. So some of the things that we're going to talk about today are collaborative filtering style recommender systems, such as, for example, matrix factorization. The difference is that they are more elaborate or they're more complicated than the ones that we have just described. So I will pass this. So for collaborative filtering, a quick summary. Collaborative filtering looks at the usage data. It doesn't care about the content of the items. It tries to find patterns within the usage data that we have. So ratings, purchases, downloads, and so forth. There are two big families of collaborative filtering methods. The neighborhood-based collaborative filtering, which we have seen there are user-based and item-based, and then a very, very big family of model-based collaborative filtering where matrix factorization, deep learning systems fit there very well. One big advantage of collaborative filtering is that we don't really need to know anything about the domain. So we only need to know the IDs of the items. The items may be textual items, documents, for example, maybe images, maybe products. We don't care. We don't need features for the items in the way that content-based filtering required. And it generates good recommendations in many cases. Now, yeah.
Can I ask a question?
Absolutely.
Yeah.
You can ask questions.
At the same time, when you try to identify users that are similar, for instance, I think it would be the same for items, you use some cosine similarity that are based on features of these users, right? On a representation description of these users.
So the question is, when you try to correlate users or items, are you using features to correlate this? For example, when you're using cosine similarity. The answer is no. When you use cosine similarity or Pearson correlation for the same, you compare the vectors of the items or the vectors of the users, but these vectors are vectors of ratings. They are not vectors of features. So that is the difference. Other questions now that, yeah, exactly. Okay. So a big problem with collaborative filtering is cold start. So if we have a new item in the system, nobody has rated this item or only a few people have rated this item, it will not make it to the recommendation lists of other people. Popularity bias is a big thing. The more we like things, these items will make it to the recommendation list to many users. And actually, this particular problem, popularity bias, was one of the reasons that specific methods for handling attacks, malicious attacks, to this type of collaborative filtering algorithms have been implemented. Because it is very easy to go into the system, create different malicious profiles, and change the recommendations that the users see in a way that is beneficial for you. So we have seen one idea of two things up to now. That in general, there are two families of recommendations. There is a content-based way of filtering, this collaborative way of filtering. And of course, in reality, we can combine both. So we have hybrid systems that try to combine the best of both worlds. Okay? And under each of these particular methods, there are a lot of different methods. So the computational methods that I described so far are the very early examples of recommended systems that we have seen. What we're going to see for the rest of the tutorial are some other examples that are actually very latest. So some of the problems of these early recommender systems were that everything is computed, at least for the model-based, everything is computed in offline mode, okay? The second one is, we already saw that scalability issues. Once you start to have a lot of users and a lot of items, these methods start to having serious trouble. And the third thing was that up to now, we were talking about ratings and maybe purchases, so pretty simple signals. But our lives and our data are more complicated now. So for example, if you go on YouTube, we have the opportunity to leverage multiple different user signals. What the user watched, up to which moment he watched this particular movie, what categories he went in, what was the sequence of searches he performed. Anything you can imagine could be a signal. So how do we incorporate all these different signals in the models that we described earlier? So based on these three big problems, we're going to discuss about matrix factorization, which was the first breakthrough in recommender systems for learning more accurate, more scalable recommendations. We're going to talk about multi-armed bandits that essentially help us learn online interactive feedback from the user and update our recommendations on the go, so we don't have to wait, accumulate all the preferences for a month, let's say, and then update our model and then compute new recommendations, but we can go with the user at the same time as the user interacts with the system. And last but not least, the last couple of years, deep learning systems have become to appear for implementations of recommender systems. So we are going to see how they are used and how they can learn from huge amounts of many different user signals. Any questions? I'm trying to just drink a little water. So. So matrix factorization was popularized by the famous Netflix prize. That was a contest that began back in 2006, lasted for 3 years, and the objective was that the winning team would get $1 million if they could improve the mean error rate for the recommendations that Netflix produced up to that point over 10%. So all top-performing models ended up being some variation of matrix factorization at the end. And matrix factorization after that changed the whole landscape of recommender systems. It became the major component of many modern systems up to now. And of course, the last few years, other methods have begun to be used in these systems, but matrix factorization is still a very important component of systems such as Netflix and Yelp and so forth. So one big thing about the Netflix prize was that for the first time, a large-scale industrial strength data set was released. So we have 100 million movie ratings by 500,000 users for 17,000 movies. That was a data set that was released. And there was a test data of 3 million ratings. And of course, a held out truth set that Netflix was using in order to compare all the different algorithms. And you can see that there was a huge number of contestants. The whole thing, as I said, lasted for 3 years. And that helped a really rapid development as the competition was really fierce for this competition. And this is, by the way, the winning team. Actually, 2 teams joined forces at the end. So we have Belcore, AT&T Belcore team, and Pragmatic House, that was a Czech, I believe, team. So what is matrix factorization without any math? So matrix factorization, the idea is that let's assume that we can describe a user with a very small set of features. Let's say, for example, that feature 1 describes how much this user likes mystery movies. In a similar way, let's assume that we can also describe each item by an analogous set of these K features. For example, in this particular case, feature 1 would tell us how much this particular movie is close to being a mystery movie. Now, having a user representation like this and an item representation, as we described, it is very easy to compute a rating of how much the user will like this item by just taking the dot product of these 2 vectors. So this is the simple idea behind matrix factorization, and this is why it is intuitive and it is also very fast. So matrix factorization essentially is inspired by dimension reduction methods such as PCA and SVD, and actually the first matrix factorization method was an SVD method. And then it evolved to the basic matrix factorization form that we know, and several extensions have been built on top of this matrix factorization formula. Now, why do we care about dimensionality? What is the problem with dimensionality? When, for example, you have 2 vectors that you want to match that describe 2 documents, and each of these vector has, let's say, 1 million of terms. You can imagine problems such as how do I store such big vectors? How do I process efficiently such big vectors? And of course, there is a lot of sparsity because not all these dimensions in each of these vectors are important dimensions. So essentially, dimensionality reduction comes to rescue, and we try to find what are the most important dimensions that can describe our items, either documents in the case of information retrieval, or, for example, products or movies in the case of recommender systems, or graphs, for example, for social network analysis, and so forth. There are many techniques that are used for this purpose. For example, LDA produces topics to describe documents. Here we care about singular value decomposition, and that is what we are going to describe next. So I see that all the sentences that start from very far, at the beginning, they miss some letters, but that's okay. So the idea of singular value decomposition is that you can decompose any matrix into the product of 3 different matrices. And since here we care about ratings, let's assume that this is the initial matrix that we have, our rating matrix, users and items here. We can decompose using singular value decomposition into these 3 matrices. This one essentially being a diagonal matrix where the diagonal values are ordered in decreasing order, and they are all positive real entries. Now, how do we realize the dimension reduction? Because in what we have here, this side gives exactly this side. So we have equality. So the idea is that we try to find a matrix that can approximate our original matrix R by taking the k largest singular values from this matrix here, along with their associated left and right singular vectors, and we discard everything else. So the result is what we call a low-rank approximation of matrix R of rank k using singular value decomposition. So essentially, if we take the product of these red matrices here, we're going to generate a matrix that is an approximation of our original matrix R. The solution here, we have a minimization problem, and the cost function that we use essentially measures how close, what is the fit between our given matrix R and the approximating matrix that we have, the optimization variable in this case, under the constraint that this matrix, approximating matrix, has rank k. So essentially, this is the result. The result is an approximating matrix that minimizes the Frobenius form over all k-rank matrices, and the Frobenius form is just this guy here. Any questions?
Would the minimum always just be using all the eigenvalues?
Sorry?
Wouldn't the minimum always be using all the eigenvalues to get the same matrix?
Good question. So the question is, if I understood correctly, of course, let me go back. So are we going to have essentially, let me rephrase that. If we minimize this function here, do we reconstruct exactly all the values that we had here? For example, if we had zeros, do we learn the zeros? Okay, so this is a great question, and the answer is no. First of all, because after, of course, several efforts, they realized that, so they did different tests. So one test was, okay, what if for these values that we don't know, we just put default values there? For example, the average for each user, or the average for each item. So they tried different things like this, and they didn't really work that well. So what we do right now is that we totally ignore these missing values, and we only try to approximate the values that we already know in this matrix. Okay?
How do we choose k?
We choose k based on many different factors. For example, k essentially describes how big our model is going to be. So that is one factor that you have to take into account, how big you can afford the model to be. Then you also try based on different numbers that make sense. For example, you cannot have something like k equal to 2 because you are not going to generate a good approximation. There is no magical number, for example, that will tell you that if you have this type of matrix, you can go with k equal to 100. So unfortunately or fortunately, you have to experiment. It depends also with things like how sparse your data is.
So in practice, what are some reasonable values for k being used out there?
For example, it could be something around from 100 to 1,000, but again, there is no magic number. So that's why when people ask me questions like this, I hesitate to give an answer because sometimes they say, oh, okay, so I will go with 100. This is not the reality. Okay? Now, once we have done this, then we can use the result, these three matrices, to predict a recommendation score for a user and for a particular item. So we can predict a missing score from this matrix R. And this would be the formula to use in this particular case. Well, the formula is nice because we can pretty easily make this computation at real time when we want to generate a recommendation for the user, but still we didn't like it. So let's see how we went to low-rank matrix factorization. So in this case here, this matrix that we had, the diagonal matrix, is actually absorbed within these two guys here. And now it is more easy to understand also conceptually matrix factorization in this way because we have our initial matrix of ratings from users and from items. And now this is a description of users based on some k latent factors. And this is a description of the items based on, again, some k latent factors. Of course, we call them latent because we don't know exactly what they stand for and we don't care. But then the minimization problem becomes easier to understand and compute as well. But also, before going to the also part, one thing that we may have trouble here is overfitting our data. And in order to avoid this, we use regularization. So essentially, the idea here is that we want, of course, to learn a model that can predict based on what we already know here, so from the observed ratings, but we don't want to overfit our model. We want to be able to generalize, because in this way, we will be able to predict unseen future ratings. So that's why we add this factor here that essentially penalizes these two matrices based on how big they are, based on their magnitudes. Now, how we choose the factor lambda? Again, through experimentation, just to answer this question. So how we train the model? We can use ALS, we can use stochastic gradient. I'm not going to go into details here. The beauty of low-rank matrix factorization is that we can simplify our problem like this. We can build a model that has k latent factors without knowing what k is, but that will be much, much smaller than our initial dimensionality of the problem. And then, this is the nicest part of all, we can compute any part, any missing rating here, by taking the dot product of the corresponding user vector and the corresponding item vector. And let's see an example. So we have here users and 3 movies. And let's assume that this is our table P that we computed, where we have 5 latent factors. As you can see, they don't mean anything. We just gave names here to be able to describe them, but they don't mean anything. And similarly, for the 3 movies, we have the same 5 latent factors. And then we can make a prediction about user 3 and Spider-Man by taking the dot product of the 2 yellow vectors, which is very easy and very fast to compute in real time. Okay. Now, there are many different forms of matrix factorizations that were developed since then. So this was the basic matrix factorization form. So in this idea here of asymmetric matrix factorization, the idea is that we got rid of the user vectors, and we only have item vectors here and item vectors here. Why do we do this? First of all, what we have done here is that we use this binary user item purchase matrix that essentially captures which items the user has purchased, and then we can rebuild the user history for a particular user by taking into account this matrix here and the items described based on the latent k factors that this matrix has. So essentially what we do here is that instead of learning two different matrices, one for users and one for items, we only learn about items. When do we do this? We do this in problems in domains where the number of users is much, much, much larger than the number of items. So this is actually a neat trick to do in order to get rid of the fact that we have too many users in the system and only work with our item catalog, essentially, which is much smaller than the number of users. And this is actually this is the actual form of matrix factorization that was used, that was integrated in Netflix after the prize. Now, so this is a matrix here, but for some reason the boundaries are not shown. So let's for a minute recall the item-based collaborative filtering idea. So in item-based collaborative filtering, we compute similarities between items based on some formula, for example, the cosine similarity of the rating vectors. And then, based on these similarities, we try to make recommendations. So the SLIM model here essentially tries to capture this idea. So we have the initial rating matrix here. We have a user item binary purchase matrix here. And then we have an item-to-item similarity matrix here that is computed by the low-rank matrix.
Can you stay closer to the screen? This is making it real small. There you go.
Okay. Okay. So here we have the item similarities. And the idea is that, so the item similarities here, of course, are computed from the low-rank matrix factorization, which means that they may capture implicit similarities between the items that we cannot understand. There is no explicit formula of this similarity meaning something. And actually, this is something really nice, because in this way, we capture underlying similarities, hidden similarities between the items, and this is what this matrix here stands for. And then to predict a recommendation for a particular item and a particular user, it is an even simpler formula than before. Yeah.
What did the second matrix stand for?
This one or this one?
That one.
This one. So this one is a matrix of items and items. Each cell here is a similarity, shows a similarity between a pair of items. And I forgot to say that, of course, the diagonal here is 0. Otherwise, it would become a trivial solution. Questions? Okay. So matrix factorization is all about discovering latent features between items and users and their preferences. It works on usage data. The basic advantage of matrix factorization is that it learns a very compact, a very nice model of user preferences, and it has superior performance both in quality, in terms of quality of the recommendations, and in terms of scalability. The big problem, because nothing is perfect in this life, and of course in recommender systems nothing is perfect, there is no way to explain why we see these recommendations. For example, in content-based, we could explain why you see this recommendation because you have liked this other movie, or because you like John Grisham that we saw earlier. Here, we don't know what the latent factors mean, and so part of the works that are being done for matrix factorization is actually to find a way to overcome this problem and explain the recommendations to the users. Multi-armed bandits. Question. No multi-armed bandits.
So in this slide, are there some works where they map the latent space with some existing features to explain the
Yeah.
recommendation?
Yeah, yeah. So, and there are multiple different ways that they try to do this. For example, using in parallel a content-based recommender system and a matrix factorization-based system, and try to see which recommendations correlate and how they can correlate them. There are many different ways. Okay. Now I feel the urge to go over there. So, but I will not, I think, or I will fall. Okay, so other question, yeah.
You mentioned three methods for matrix factorization. So how do you compare the three? Which one works best in practice?
It depends on your problem, it depends on the domain. For example, This one here, the asymmetric matrix factorization, again, there are no magical rules. I will repeat that every time it is pertinent. But this one, for example, it makes sense to use it when the number of users that you have in the system is much, much larger than the number of items. If that is not the case, then it doesn't make sense to use it. You don't earn something, you don't benefit from this method in any way. Slim, on the other hand, it has the advantage that it learns through implicit item relationships, and it is a great method to use along with other methods. For example, you could use it along with the content-based filtering that captures the content similarities and the content preferences, so you can use them both and have a better recommender system. Again, there are no recipes, there are no magic solutions here. For each problem and for the domain that you have, the first step that you do is actually to, if you are a company, you have a data scientist to go into the data, look into the data and see what the data tells you, and then start with the method that makes sense. And I will come back to this later when we go to deep learning methods, because it is also relevant there. Okay. Multi-armed bandits. So what is a single-armed bandit to start with? So single-armed bandit refers to a slot machine in a casino. And so the multi-armed bandit refers to a row of slot machines in the casino, but the multi-armed bandit problem is a very well-known problem from probability theory and refers to the following situation. Imagine that you have a gambler sitting in front of a row of slot machines, and he plays, of course, the different machines, he pulls the different levers. So the problem here is that when the user plays a machine, this machine returns a reward. The reward, of course, comes from some distribution that is specific to this machine, but of course, unfortunately, is unknown to the user. So the gambler wants to find in which order and how many times he needs to play the different machines in order at the end to gain as much money as possible, and at the same time lose as little money as possible. So essentially here there is a trade-off. There is a trade-off between exploring the different machines in order to understand what are their payoffs, and exploiting the current knowledge that you have and play the machine that you think it is best right now. And let's see a very simple example. So these boxes are machines, okay? And as a gambler, I have a model for each machine in my mind that I keep for the rewards. So in this particular case, the numbers here, for me, they represent how many times I have gained a reward from this machine out of all the times that I have played. So for example, this machine here, 70% of the times I got my money back. So that's a good machine. While, for example, this machine here, only 35% of the times gave me back a reward. So this is a reward model that I have, and at the same time, I have an arm selection strategy, which tells me, okay, now which machine I'm going to play next. For example, one could say, go with this one, because it seems the optimal, so this would be an exploitation phase. Someone else could say, no, you need to explore more. Maybe you should go with this one and see, maybe it is a better machine than this one here. So you need to explore, but maybe at the risk of losing money. And of course, the exploration versus exploitation dilemma is very well known in many scenarios, from your everyday scenario where you want to go to a restaurant and you can go with your best restaurant, your favorite restaurant. So in this case, you are exploiting your knowledge. Or you could try a new restaurant, so you would exploring a new choice. But also in more serious problems, for example, in clinical trials, where the researcher wants to find out what is the benefit of its of specific treatment, but of course minimizing the losses. And of course, in scenarios like this, exploration-exploitation is a very important dilemma. So what is the multi-armed bandit problem? We have a set of arms or actions, and the algorithm proceeds in discrete trials. So in each trial, it considers the current context, and it chooses one arm to play. And for this arm, it receives a reward. So then it uses this triple here, the context, the arm, and the reward, to update the knowledge that it maintains for this particular arm. In the long term, we want to minimize regret. And the regret here is essentially the difference between the total optimal rewards the algorithm could have gained if he had made the perfect choices, and the rewards that he actually received because he made the choices that because it made the choices that it made. And in the simplest case, the multi-armed bandit problem called the context-free algorithm problem is when the algorithm has a constant set of actions, so a constant set of arms to deal with, and the context is the same, doesn't change across the different trials. And let's see a particular example to understand what all this is about. So the set of arms could be, for example, a set of news articles or a set of advertisements that we want to display to the user. The context is the user demographics, the location of the user, the device of the user, things like that. The reward, when a particular advertisement is shown, is, of course, whether the user clicked it, then the reward is 1, or didn't click it, then the reward is 0. And the total reward is, of course, the total click-through rate. And what we want to do here is we want to maximize the expected number of clicks from users, which in multi-armed bandit language means maximizing the total expected payoff. So there are two components in any multi-armed bandit algorithm. The first component is the arm selection strategy. How do I select which arm to play next? And the second component is a reward model. What is my knowledge and how do I improve my knowledge of the reward that each arm can give back to me? And a very simple, of course, model could be this one here that essentially counts what were the rewards over all the times you played this particular arm. Now, let's go and see some particular examples of multi-armed bandit algorithms, starting with epsilon greedy, a naive approach, but still valid in many settings. So here we have a context-free k-armed bandit problem, which means that we don't have context, and we have a fixed set of arms. For example, we have a fixed set of advertisements that we want to recommend to the user. And the epsilon greedy actually works in a very simple way. In every trial, it computes the average payoff for each arm, and then with probability 1 minus epsilon, it chooses the best action to show to the user, so it will go on an exploitation phase. And with probability epsilon, it will choose a totally random arm to show to the user going on an exploration phase. So this is how the algorithm works. And if we want to take a look at a simple epsilon greedy algorithm, we have the initialization phase here. This is the initial reward for each arm, and we assume that this is 0. Our knowledge is 0. The number of times each arm was played is again 0. This is the arm selection policy that we just described. And after the algorithm receives a reward for the arm that it played, it uses this reward to update the model here. In this particular case, we used a simple Monte Carlo evaluation where we adjust our knowledge about the reward of each item based on the difference between our current estimation and the actual reward that we received from the user. Easy to implement, guaranteed level of exploration. That's on the positive side. On the negative side, however, we have unguided exploration because the algorithm picks randomly items to show to the user. So we don't necessarily know what is being explored and with what is the reasoning behind it. It is totally random. And then the other problem is that epsilon is always constant. But in reality is that the more we interact with the user, the more preferences of the users we collect, the more we understand the user. So maybe at the beginning it makes sense to start with trying more exploration efforts. And as we learn, we should try more exploitation phases. So epsilon should change in this way.
Does this kind of algorithm come with any guarantee, like after certain number of times you find out?
So it has a linear total regret, yes. I'm oversimplifying the math here, but we don't have any other option. So any other question for epsilon greedy? So another big family actually of algorithms are called the so-called optimism in the face of uncertainty. And here the concept, the philosophy is the following. The more uncertain we are about a particular item, maybe this is more important to explore this particular item. In this way, we have two chances. One chance is that this item is, of course, the optimal. So, yeah, we went with the optimal item. If it is not the optimal item, still, we learned something about this item. So, our uncertainty about this item is decreasing. And by doing this repeatedly, we can finally home in on the best action. So, let's see how that goes. So this family of algorithms, they are all called upper confidence bound algorithms. And the idea is that we compute an upper confidence value for each action such that the actual reward for a particular action is bounded by our estimation and this upper bound UT. And when we choose our arm selection strategy essentially, is the following. We select the action that maximizes essentially this quantity here, or it maximizes the upper confidence value here. Now, how do we compute? What should be this UT, this upper confidence value for each arm? The idea is the following. When we start our experiment, we are uncertain about every item, essentially. So essentially, when we have played only a few times a particular item, that means that our uncertainty is higher. That's why this value should be also higher. The more we play a particular item, then the more we learn about it, which means that our uncertainty goes down, essentially. And that is what should happen with the upper confidence bound as well. So UCB1 is one algorithm from this family of UCB methods that gives this confidence interval for the selection of the items. So, question. So the positive thing about UCB algorithms is that here we have guided exploration, essentially, and the guided exploration is towards the most promising arms. Promising arms in the sense that either they are optimal or we have a great uncertainty about them. So if we try them, we will decrease our uncertainty, and this is a good thing. It has good theoretical bounds. One advantage is what we call the delayed feedback. This type of algorithms, and epsilon greedy belongs to this category actually, is that they need to update their model every step. So you cannot, for example, collect 3 rewards from the user and then update the model. It will break. So they need to update for every reward, for every action, on every round that the algorithm runs.
So how is it that you're making a recommendation? Does a person need to have the same experience or do the same action repeatedly? So are you clustering items so that you can pick one out of a cluster, or what do you do?
So the question is, how do you use this kind of algorithms to make recommendations essentially to the users. So right now we want to learn about these algorithms, so I haven't still talked about how we use them for recommendations. So, but the objective of each algorithm is that given a set of items, for example, a set of products, and a set of users, you can let the algorithm play with the users and try different strategies, for example, this one here, and learn the user preferences for each item over the whole population or over, it depends on how you want to set it up. And we are going to see specific examples in a while, okay?
I'm missing something here. How does this relate to the recommender systems applications that we described in the previous part of the talk?
So bear with me for a couple of slides, okay? But let me repeat here that imagine that you have a set of news articles that you want to show on the front page of your system. These news items come and they are always fresh, so you don't have information from the users already. So essentially, you cannot use any of the traditional recommender systems that they say, okay, let me start looking at what the users are doing in the system. At some point, I will be able to learn a model. Based on this model, I will make recommendations. I will keep collecting feedback and so forth. So here we are dealing with a totally different situation. You come up with a new set of items, and you want to recommend them. So you want to figure out which of these items you're going to show to the users and which users. But right now, you don't have the luxury of waiting until you collect information from the users. So in these multi-armed bandits, essentially, they give you the ability to learn as you go and adapt as you go. And also in, let's say, 20 cycles, you can generate some initial model about what the users prefer or not, which is not possible with other recommender systems that have, they need to collect a lot of information. This information should not be sparse. You have to wait, essentially, until you are able to make recommendations.
One very quick question. So new items, new articles are becoming available all the time. What about the old ones? Do they expire at some point, or they keep being candidates?
It depends on the problem that you have. But when you have the old items, essentially, you collect information about them. So these are not your problem. So if they are popular, you can say, okay, they are popular. On the other hand, if they can expire, then you also want to be able to learn this information as it is happening. So if, for example, a news item, its popularity is going down, based on what you have known so far, because people clicked it, let's say, 1,000 times, you would say, okay, this is a popular item forever, which is not true. So you need to start understanding that they didn't click it, and your model should start adapting immediately. These models can do this.
Right?
They can do it, yes.
Just based on your previous answer, do you assume that the new items have features that you have never seen before in the old items?
It may be the case.
Okay, but that was not your assumption, because you say you cannot know, you cannot learn any knowledge based on the new items because they are completely new, but they may have features that you have seen before, right?
So it depends. Okay, so there are two ways to use this. Either you ignore the features, so you don't have context. So essentially, what we are talking about right now is no context. So you don't have context or features about the user. You don't have context or features about the items. But you can also have, and that makes it a contextual bandit, which essentially learns information about clusters of items. So if a new item comes but belongs essentially to a cluster, it can benefit from information that the multi-armed bandit has already acquired. Okay? Okay, let us assume that we have an item, we have shown it 10 times, and 1 is when we had a click from the user, and 0 is when we didn't have a click from the user. So epsilon greedy and UCB, they are frequentist approaches because they would say, okay, I estimate that the true payoff for this particular item is somewhere around 0.5 with some confidence value, okay? Now, a Bayesian learner says, I'm not so sure about it. So instead, a Bayesian learner maintains a probability distribution about the reward of each item. And the probability distribution essentially tells, for each possible reward value, what is the probability that this value is actually happening for this item. And we have the knowledge of the user at the very beginning, at point 0, and this is what we call the prior knowledge or the prior distribution. And then for each observation that we collect from the system, we learn the posterior distribution based on what we have observed so far. Now, there are two big families here, the Bayesian UCBs and probability matching, and especially for probability matching, I'm going to talk about Thompson sampling. So let's assume again that we have no context, that our arms are independent, and let's assume that for each arm, the reward distribution is a Gaussian. So for each arm, we have a mean value and a variance that describes how the reward distribution is shaped. And let's view this through an example. So we have here 3 items, A1, A2, and A3. So A3 has a high mean value and essentially low variance, low deviation, and that actually is a good arm to exploit because it looks like it has a good reward, and we are pretty sure about that this is the reward that it's going to give us. On the other hand, if we look at, for example, A2, the red line here, it has a lower reward, mean reward, and also we are pretty uncertain about this value. So essentially, in the UCB way of thinking, this would be a promising arm to explore because we can learn something about this arm that we didn't know so far. So essentially, the prior here is we start with a Gaussian probability about the reward for each arm, and then when its new observation comes in, we update our model by applying the Bayes law. And then our arm selection policy essentially is the following. We pick the action that maximizes the standard deviation. And we see here how that fits into our model. So this is how we pick the most promising arm in a Bayesian UCB algorithm. Now, I'm switching gears. I'm going to probability matching. Now, in probability matching, we want to choose the action that most probably is the best action to go with. And the good thing about probability matching is that we do not have to tune some parameter, but that the whole process evolves as we explore and exploit in the different rounds. So Thompson sampling is a method that was actually proposed in 1933, but it became famous and very popular in recommender systems only a few years ago, when there was a seminal paper that actually ran evaluations with Thompson sampling, UCB, and other multi-arm bandit methods, and it proved that this heuristic here is able to generate reasonable recommendation. It is very efficient and also very scalable. So the idea here is that we have a prior that is given based on, that depends on some coefficient vector theta, and the posterior also depends on this coefficient theta. For example, the reward of an arm could follow a Bernoulli distribution, so our theta parameter here is just the probability mu, which tells us that the reward will be 1 with probability mu, and with probability 1 minus mu, it is going to be 0. So the aim here is that we want to learn the model probabilities for all the arms that we have in our arm set and generate the best and find the best arms. So starting with, for example, the Bernoulli distribution, other options, for example, would be to use a Gaussian distribution, but let's assume that we have a Bernoulli distribution here. Now we can assume that the prior knowledge of the algorithm with regards to the parameter mu is given by the beta distribution. So the beta distribution in general has two parameters, alpha and beta, and thereby essentially control the shape of the distribution here. It is common to use the beta distribution to model parameters that have a range from 0 to 1. That's why we use it here as well. So essentially, at time t, the arm wants to play the arm that has the highest probability of being the best. So we want to solve this. And of course, once it plays the arm and updates and gets back the reward, it can update the beta distribution very easily like this. However, the problem is this guy here. How can we avoid the direct calculation of the integral that hides behind this formula? And the heuristic of Thomson was the following. Let's just generate a sample from all betas, so from the beta for each arm, and pull the arm whose sample is the largest. So this would be a Bernoulli bandit with Thomson sampling. I will not go into details for the sake of time, but the idea was, we discussed the idea. But let's see an example. So let's say that the probability distribution here is just a function that returns the probability that the click-through rate is of some particular value. So for each arm, essentially, we pick a random click-through rate from our current belief of its probability distribution, okay? Then we sort the articles based on the samples, and we pick the article that has the highest sampled CTR. The Thomson sampling, good empirical performance, there is no tuning, it is robust to delayed feedback, so it can actually wait and get some feedback before updating the model that will not hurt the accuracy. Now, going to the earlier question and how all these fit with respect to recommender systems. 3 ways that multi-arm bandits are used for recommender systems. One is for popularity ranking. How essentially do we learn preferences about new items, and how do we balance the exposure of these new items with the old winners, the most popular items, and so forth. The second is that we can combine these in model to have model-based collaborating filtering. For example, we can use UCB scores or Thomson sampling to generate recommendations for users in a collaborating filtering way. And last but not least, we can use the so-called dueling bandits. We can use a multi-arm bandit in place of A/B testing. So when we have 2 recommendation methods and we want to compare them in real time, we can actually have them shown to the user at the same time and have a multi-arm banding sitting behind the scenes and learning which items, essentially which items coming from which recommender system the user is choosing. So at the end, the multi-arm bandit will make a decision which recommender system is best. And this is a great way to avoid A/B testing altogether. So let's see an example for popularity ranking. So many content providers have repositories with content such as news, ads that change very frequently. And not only the content changes very frequently, but also the popularity of the content may change over time. Also, the visitors that visit the place, the website, may have no historical consumption information record in the system. So all these issues essentially make traditional recommender systems not applicable or very difficult to apply. Now, why do we want to use a multi-arm bandit? because essentially it can very naturally handle uncertainty due to item churn. It can learn directly from user feedback. It can cover more items, a greater part of our catalog in this way. And it also allows for faster experimentation. So instead of waiting to collect as much information as possible to learn a model and then to experiment with the model, the multi-armed bandit can do essentially all in one. Of course, what we're talking up to now was theoretical, but now we're going to deal with users. And here we want to be able to collect information from the users, which means that we may dissatisfy the users in a short term, but at the same time, we want to maximize user satisfaction in the long run. So we have these two competing goals, and at the end of the day, we want to leave the users happy, not unhappy. So let's see this example here. This is the Yahoo news page, and we have the featured news article here. Behind it, there is an hourly refreshed article pool curated by human editors. In this particular example, the pool is pretty small, but it is updated in every hour. And the average lifetime of an article is also very short, from 6 to 8 hours. Users come and go, so we are talking about a very dynamic user population. And the objective here is we want to be able to learn how to rank the available articles according to how users like them and highlight the most attractive, the most important article for each user in this particular story position. And let's see how we can use a multi-armed bandit to solve this problem. So first of all, we split our live traffic in two buckets, or at least two buckets, if you like. One is where we have the multi-armed bandit, so this is called the learning bucket, and this is where the multi-armed bandit experiments and learn. And the winners, what the multi-armed bandit learns from here, are used for the serving bucket. And it may be the case that whatever we learn there, we show everything to the user, or we combine it with previous more popular items, and we use a hybrid method there. It doesn't matter. Now, the first way to do this is to say, okay, I can use a UCB or an epsilon greedy, just one algorithm, one instance of the algorithm, no use of features, nothing. I run this instance over the items that I have and over the whole user population, and I learn preferences for these items over everybody, essentially. So this gives no personalization, this has no context, no contextual information about the items. The second option is to actually consider that users and items have features. So for the features, we have demographic information, geographic features, and also behavioral information that comes from the site. And for the items, we have URL categories and editor categories. And what we do is that we partition users into 5 groups. We partition items also into 5 groups. And then in each user group, we run a separate copy of a multi-armed bandit. So this multi-armed bandit will learn preferences of this group, another one will learn preferences for the other group, and so forth. Then the other option is to use actually a contextual bandit, a bandit that understands about features for the users, features for the items. And one such algorithm is the lean UCB. So what is the idea behind lean UCB? The idea is that the expected reward for an item, given a particular context, is a linear function, taking into account the context, but also some unknown coefficient vector theta. And at every round, t, we maintain all the contexts that are observed previously when the item A was played, and also we maintain all the responses that we collected for this particular item when we played this item before. After ridge regression, we end up with something like this, But then the lean UCB essentially picks the action, again, that maximizes standard deviation, where standard deviation for this particular case is given by this factor here. And the actual lean UCB algorithm has some nice features. For example, it can work with a dynamic set of items. So as new items come and are added in the pool, no problem. It can start learning on these items as well. Then it can estimate the coefficient very easily from this line here. And also it can incrementally update the two parameters here, where the two parameters essentially are this one here and this one here, that give us the estimation of the theta value. And it is a great algorithm actually to use in practice. So it works well with a dynamic arm set. It has complexity, linear complexity, and so forth. So summarizing over multi-armed bandits, these are problems that are well known before even the recommender systems were invented, but they have great applications in recommender systems the last essentially 2 or 3 years. One recent example where a multi-armed bandit algorithm is actually used, you can find it on Netflix. On Netflix, every image for every movie, there are multiple possible images that can be shown for this particular movie, okay? Now, the objective here is to learn which of these images would be more attractive for a particular user and make this user click and watch this movie. So the particularity of the problem essentially calls for a multi-armed bandit, because we need to learn over unknown information, over new users, new items for this particular instance of the problem, and the multi-armed bandit algorithm works very well because it can understand when the popularity of a particular image goes up, when it goes down, how different users react, and so forth. There are, of course, some concerns and that still haven't been solved. The size of the repository is a problem. So, for example, in the case of the contextual lean UCB that we described earlier, we divided the items into groups. So essentially, we were talking about 5 items or item groups that the algorithm had to deal with. The lifetime of items, so if an item has a very short lifetime, it may be not enough even for the multi-armed bandit algorithm to learn something and react. And performance is still something to figure out. Multi-armed bandits have a lot of theory behind them. Their applications recommender systems are quite new, so we need to figure out how to make them scalable and how to use them best in practice. Any questions? Last but not least, deep learning systems. Deep learning methods are paving, there's a lot of hype behind deep learning methods for image processing, for natural language understanding and translation, for games, and so forth. But the reality is that only the last couple of years, deep learning systems became to make their way into industrial settings and into recommender systems specifically. So for image processing, for example, deep learning methods have achieved accuracy that lately is even close to human accuracy. So here we have the ImageNet large-scale visual recognition challenge. ImageNet is a large, huge, actually, ground truth data built on WordNet. So for each noun in WordNet, there are several hundreds of images assigned to this noun. And the challenge every year is how to classify and how to use computer vision initially, but now deep learning methods for image processing and image recognition. Now, What is deep learning? Deep learning is machine learning. So it is a special, a subset of machine learning algorithms that use a cascade of multiple non-linear processing layers. And essentially, they can learn at each layer a higher level representation of the data from the previous layer. And in this way, they can create a hierarchical representation of the data that we have. How deep is deep? Again, there is no magic answer, and it depends on the problem, and you need to experiment. Here are some well-known examples. The winner of the challenge, of the ImageNet challenge for 2012, AlexNet, had only 8 layers. In 2015, ResNet had 152 layers of neurons. So what is the difference between machine learning or traditional machine learning and deep learning? One big difference is in the way that we treat features. In traditional machine learning, the engineer or the researcher needs to think what are the right features to feed the machine learning algorithm and train it. Now, in deep learning, we have the opportunity actually for the algorithm to learn and to extract these features and feed the classifier for the particular problem. So this is a big, actually, a big difference between these two guys. And let's see a particular example. So starting from the raw pixels of an image, a deep learning network, for example, could first come up with the edges at the first layer, if you like, then come up with parts of objects, then come up with object models, and then finally use this to classify different images over to different classes. The basic unit of a deep network is a neuron. You probably already know that, which is extremely inspired by the neurons that we have here, up here. So it is a computational, of course, model, nothing too complicated as what we see here. And the idea is that this neuron here is fed signals from other neurons. The signal of its previous neuron is adjusted through a weight, and these weights is what we learn when we train the network. And there is here a function that if this input exceeds a threshold, then this function generates a signal in the output. For example, it could generate something like that. So these are different examples of activation functions. This was one that was used in the old days and had several problems. The most important one being that it was very hard to train the model because it would kill the gradient and then that would be the end. One of the latest advances in deep learning was actually the invention of the rectified linear units. And they are very popular. They are used very much in deep networks right now because they are fast. They don't have the problem that this guy here had. They have some other problems themselves, such as how you tune the learning rate. But overall, they were one of the great breakthroughs in deep learning the last few years. Let's see some examples of deep networks, and then we're going to see some particular industrial examples of deep learning networks how they are used in practice. So a fully connected feed-forward network, you have layers of networks. Each layer is fully connected to the next layer, but you don't have anything happening here. So there is no neuron connecting to any other neuron in the same layer. A recurrent neural network, essentially, you have multiple copies of the same network here, each one feeding a message to the next one. And recurrent neural networks and their advanced version, if you like, LSTMs, are very nice models to use for sequence modeling. In the case of recommendation for learning sequential recommendations, if the user has done this, this, and that, what is he going to do next? So these are recurrent neural networks, but more importantly, LSTMs are the ones to use. And just a funny application of recurrent of RNNs, they can generate fake Shakespeare documents. They can generate fake LaTeX code that almost compiles. So you can use it for becoming a writer. Convolutional neural networks, they have great application in image processing, for example, for object identification, for segmentation, and so forth. Let's see the idea. We have 3 steps in a convolutional operator. So our input here is an image. In this particular case, a 5x5 image. And this is a convolution filter that runs over the image, okay? And essentially, as we slide it over the image, we compute, we multiply every cell of the operator with the underlying cell from the image, and then we sum up everything together. And in this way, we generate what we call a convolved feature. For example, we could use one filter that helps us detect edges. So here, this would be essentially information about the edges found in this particular image. Then the next step is to add a rectified linear unit function there, because what we did so far was just a linear operation. So we want to make this non-linear, because our data, in most of the cases, comes with non-linearity. So that's why we add this level here. And the next and final step is pooling, where essentially from what we have produced so far, from the convolution filter and from the rectified linear unit, this is the output so far, and we perform a dimension reduction step. For example, we take the maximum value from each of these regions here, and this would be the final feature map that we generate. This is a very high-level example of how a convolutional network can be used in practice. So here we have the convolutional network is this part. Essentially, it generates all the different features that we need, but we don't know, of course, in order to classify different images. And then we have a fully connected feed-forward network that uses these features to identify whether the image here is a dog, a cat, a boat, or a bird image. So this is why convolutional neural networks are so important, because they can extract from raw data, they can extract features that can be then used for, by a deep learning network. Denosing autoencoders, the idea here is that this guy here can take a corrupted version of the data and it can reconstruct the perfect data in its output. How is it able to do this? The idea is that during training, we take our data and we create several noisy versions of the data that we have. So we feed our noisy versions here, and then we force this guy to learn the compressed representation here, and then generate the original, without noise, data in the output. Okay? Now, deep learning had a very slow uptake in recommender systems, but they soon realized that there are great benefits for using deep learning methods in recommender systems. First of all, this deep learning offers opportunities for generalizing from the knowledge that we have that is not this, at a greater level than other recommender systems can do. It gives us the opportunity to treat and to leverage many different types of user signals, even the images and the videos that the user has consumed. These can be fed into the deep learning network. Also, we can use such deep networks such as RNNs or LSTMs to make sequential recommendations. And for example, we want to predict what the user is going to purchase next, or what movie the user is going to watch next. So this type of recommendations, you need to have to keep the sequential information about the users. And now let's see some particular examples of how deep learning systems, of some particular examples of deep learning systems. So one of the very first examples is a collaborative denoising autoencoder. It is an autoencoder as we saw earlier, so essentially it is this guy here. And now the idea is the following. In the input, you have all the items that you have in your catalog. And in the output, you also have as many nodes as the items that you have in the catalog. And now you assume that the preferences here essentially, let me say it in a different way. So these are the user preferences that you have for this particular, for a particular user, for all the items that you have in the catalog. And these are essentially a corrupted version of the perfect knowledge of the user preferences over these items. So essentially, you assume that you can train this autoencoder here in a way that when it is represented with some user preferences in its input, then it can generate the full user preferences in the output. Let's see what happens in training time. In training time, we have information about what the user has liked or which items the user has purchased in the past or which movies he has watched in the past. So we take for each user this information and then we create different noisy versions of this information. One way to create this noisy version is to, for each of these items here, with some probability Q, turn the preference into 0, essentially nullify the preference of the user. By doing this, we force then the network to reconstruct the original user preferences before we corrupted them, and in this way we train the system. Now, once we train the system at serving time, when we feed the system with the preferences of a user that we currently want to serve, this system will make predictions about items that the user has not seen, but he would like to see as well. So the system will predict more preferences about this particular user.
So your neural network is trained for a specific user, yes?
It is trained for all the users. The only difference is that for each particular user, you also keep this. So all these parts of the network are the same across all users. You only keep this special node here that is specific to each particular user. So that is the difference. But the rest of the network is common for all users. So let's talk now about wide and deep models for recommendations. So traditional recommendation systems are very good in memorizing things about users and user preferences. So for example, they can memorize very well cross-product feature transformations. So the user like this and that, and the other combination. On the other hand, in many cases, of course, we want to be able to generalize from the information that we have and, for example, find other implicit connections to items that the user may have liked. And this is where deep networks actually do a very good job. So essentially, for recommender systems, we want to combine both properties, both functions. So we want to be able to use memorization because in this way, we are going to recommend items that are similar, that are very relevant to what the user has done in the past. But we also want to be able to generalize our knowledge because in this way, we create diverse recommendations. So the way to do this is actually to co-train a wide and deep wide network. And let's see how this is particularly done for the Google App Store. So the Google App Store, of course, recommends applications based on the application that you are currently seeing, or essentially based on your context, which may be what was your previous search, or what was the application you are currently watching, you are currently examining, and so forth. So here we have two parts. So this is the wide network that essentially is just a very simple linear model that takes into account raw information such as what are the applications that the user installed, what are the impressions over applications for this particular user, and so forth. And also it takes into account cross-product transformations of these features. For example, for this type of applications in this particular context, the user always likes this. So this is a combination of features that will be fed into the wide model here. Now, on the other side, we have a deep network here that is a feed-forward network with three layers, each one containing this number of neurons, okay? And we feed several different types of data here. Continuous features such as the age, the number of installations that the user has done, but also categorical features. For example, the device of the user, demographics of the users, and so forth. Of course, before feeding this information into the system, so the categorical features, these are sparse data, and we don't want to feed sparse data into the network. So what we do is that we convert each of these categorical, high-dimensional categorical values into a low-dimensional, dense, real-valued embedding vector. And essentially, these embeddings here are smaller, deep networks that are also co-trained together with the rest of the system. Now, the continuous features and the embeddings of the categorical values are all concatenated together to create one big vector that has around 1,200 dimensions. And this is what it is fed into the deep network here to train it. Now, the output from the deep network and from the wide network, okay, the two outputs are combined together to make a prediction, and this prediction is fed to a common logistic loss function for joint training. So one thing that we need to remember here is that in recommendations, it is often the case that we use a lot of different algorithms, and then at the end we combine their results to make one recommendation list. This is not the case. So we're not talking about a hybrid or an ensemble of different recommendation methods. We are talking about one big network that has, of course, three different parts, essentially. The deep network here, the wide network here, the embeddings here, but all of them are trained together, okay, not separately. Any questions? Yeah.
So the training is done in advance of needing to suggest a recommendation.
Yes.
Right? So is the training updated?
Of course.
So is that a real-time update, or is it just a sort of every night kind of update?
It is kind of an every night update.
Okay. The other question I had was from the previous stuff was how much data do you need to fuel one of these deep learning nets?
So the question is how much, I forgot to repeat the previous question, but this question that I didn't forget to repeat is how much data you need for a deep learning method. And it's actually a great question, and one common mistake that we see when people try to use deep learning methods. So deep learning methods work when you have really a lot of data. And this is their advantage, and this may be their shortcoming if you don't have too much data. So, for example, we see startups that they have some type of recommendation problem, and they say, okay, let's use a deep network to solve the problem. And then they realize that they use a deep network, but the results that they get are devastating, essentially. And the reality is that they have so little data that these models cannot work. So these models are good when you have a lot of data, and actually they are hungry for a lot of data. This is where they excel. if you don't have a lot of data, all the other methods that we have discussed may be more appropriate for the problem that you are dealing with. So it depends on what you have to do, how much data you have.
Is the inverse also a consideration? Meaning, could you run into overfitting issues?
Always.
So there is such a thing as too much data.
Even when you train a very simple machine learning model, even when you have the matrix factorization that we saw earlier, you have to take care of the overfitting. So you don't want to, essentially, you start from your, let's say, ratings, just to make things simpler. And then you can come up with a model that predicts exactly all the ratings, but nothing else. So you failed. Okay? So that's why, for example, in matrix factorization, we show you do the regularization process, trying to make the model more flexible, more generalizing.
So basically, the overfitting problem is not because you have too much data, it's
No.
because you run far too many iterations on the same training set.
More or less, yes. And more or less meaning that you can fit even when you have very few data, very little data. So it's not a matter of how much data you have, it's a matter how you train your model on the data that you have. And actually, having less data, you have a higher risk of overfitting because you say, okay, I see 1 and 2, so yeah, that's it, which is not the case. YouTube. So YouTube up to 2016, their system was essentially a matrix factorization engine that had a lot of different matrix factorization algorithms, but it was a matrix factorization engine. And then in 2016, when they published also the paper, they redesigned the whole system. They got rid of matrix factorization completely, and they had a deep learning solution. And let's see some of the particularities of the YouTube domain. And this is actually a very good example because we see that what we were saying earlier, depending on your data, on your application, this will tell you what challenges you have and which algorithms you need to pick in order to solve it. So, scale. So, the repository essentially for YouTube is so large that many of the traditional algorithms, many of the algorithms, not traditional, many of the algorithms, the recommendation algorithms that we know, cannot cope with. Another big problem is that new content is being uploaded every second. Lots of new content is being uploaded every second. So we need, or they need, to be able to generate recommendations for this fresh content before it becomes too old. So fresh content should be recommended while it is still fresh. And also, it should take into account how the users interact with the content. They watch this, they search that, they jump from this category to the other category. All these different things that the users are doing with the system should be taken into account. Last but not least, there is no ground truth data. If you want to evaluate your recommendation algorithm or any machine learning algorithm, if we are talking about machine learning or deep learning, you need to have ground truth data so that you say, okay, this is my ground truth data. Let's see how many of these things I'm able to predict. For YouTube, users rarely actually say their opinion. There are no metadata or descriptions that could be used about the videos, okay, or an ontology or a taxonomy or anything. So essentially, we're talking about a very noisy domain with no real actual information that can be used from the users. So the YouTube recommendation model has two parts. Each of these parts is a deep learning method, is a deep learning network. So the first part here goes over all the videos that exist in the video repository and tries for each user to generate a few hundreds candidates that can be used for recommendation. Then the ranking is yet another deep learning network. And from these candidates here, it finds just a few that with high probability, they're going to be a good fit for this particular user. So let's see the first stage, okay? So this deep network here, the objective of it is to learn essentially some user representation for each user based on the history of the user and based also on the particular context. Context may be that he was browsing this particular category or that he was watching this particular movie when I wanted to show these particular recommendations and so forth. Now, let's read the figure from bottom to up. So here we have the input, which essentially is what the user has searched or what videos the user has watched. And again, here we see the idea of embedding because we want to be able to have so many different video IDs. We want to be able to generate one compact representation that captures what the user has, which videos the user has seen. So essentially, each of these are embeddings of the video watches that the user has, of the sequence of video watches of this particular user, and the same happens with the searches. We take the average to combine all these different video watches together into one vector, and then we concatenate everything to give as one vector to give to feed the deep learning network that we have here. So essentially, we use features such as the age or the gender of the user, the geographic location, but also embeddings of all the video that the user has watched, all the searches that the user has seen. So again, as in the case of the Google App Store model that we described earlier, the embeddings and the deep network and the learning that is happening here, all these are learned together and in one training session. And then, so when we train this model, what we end up having is we generate essentially an index of all the nearest neighbor videos for each user. So for each user, we generate all the possible nearest videos for this particular user. Now, so essentially what happens at serving time is that we just need to make a lookup, and for each particular user, we just need to generate the top N candidate videos. So one question earlier was how deep is the deep network. So here we have an example, we have an experiment where they have used networks with different depths, and you see for different depths how many neurons have been used at each layer. And in this graph here, they also show the effect of the different input signals. So for example here, only the watches of the users have been used. Here, watches and searches have been used. And then in this final green line, they used all the features that we saw here, that we see here as input in the system. And you see that they found the best results. By the way, the scale here is a little small, but the numbers here are, so it is a mean average precision. The numbers is 8, 10, 12, 14, so it is not that high. Stage 2, the ranking. So from the candidates, how do we generate the final results for the user? Essentially, the idea here is a similar deep network. The only thing that is different is the features that we use for this, for input to this guy. And here, essentially, the figure tells only a few examples. They use several hundreds of different signals, impressions, categories, timestamps, when did it start to play the particular video, at which point he stopped the particular video, did he forward back and forth. So all things that you can imagine are fed into this network. So essentially, if we compare these two networks, the difference between these two is that here we're dealing with all the videos, but with fewer dimensions, if you like. Here we're dealing with only a few hundreds of videos, but a lot of different signals. And at this point, I think we are over past time, so I would just like to thank you for being here so late. And if you have any questions, I will be glad to answer now or tomorrow, or whenever you would like.